how the data.
Okay,
Yeah,
so
I couldn't get into it.
you had the same problem. Was anybody able to complete it?
I was able to complete it.
I completed it
Here's
too,
the
but
issue.
I did have the same
You guys
problem.
are about to kick yourselves. If you click the Lab 4 assignment, the data is in there.
Oh, I didn't know that was the same. I thought we were missing something. Okay, because I opened it up and I still could get Excel, like that whole like the male female. I could get that. Is that what we needed?
You do need that. So here's what it should look like. Let me just share my screen. Was it this? Hold on. Okay, now I'm everything locked. Okay, hold on. So I think if you go, this should work. Is that how everybody else did it? Through the assignment, click the link there.
Yeah, that's what I did.
Okay.
Okay, so that works for me. Is it okay to still hand it in by midnight?
100%. I just want to
Okay.
screen share so you guys see what I did. Okay, so if you go into Lab 4, okay, let me back her up one more step. So if you go here for this week and you click Lab 4, and then it's right here, it's this Excel spreadsheet. If you, oops, people are trying to get into the class here. If you open it, okay, and you guys are not gonna see it again because it opened on my other screen. Can you guys see this? Lab 4 data?
Yes.
Okay. Yep. So there's gender. Do you, more or less now that you're in college, have you gained or lost weight? When do you snack? Would you say you eat more or less? And age. So going back to what we're asking for the lab, you have to do 4 analyses. You need to include 1 mean, 1 median, 1 standard deviation, and 1 crosstab. Okay. So let me bring up the data set again. In order to do a mean, median, and standard deviation, what do you need? Do you need categorical variables or do you need interval ratio?
Interval ratio.
Right. And how many of our variables are actually interval ratio?
Only age.
Only 1. So this was my way of trying to be nice because you guys just need to use this variable to do mean, median, and standard deviation. For the crosstab, you can pick whatever you want. That's why I included all these extra ones, which are kind of fun, interesting variables. So you can do a crosstab and see if there's a relationship between each. Does that make sense?
Yes.
Yeah.
Okay.
Thank you.
Yeah, no problem. So yeah, up until midnight, just let me know, submit it, and we'll go from there.
Thank you.
Okay, I want to make sure that I feel like I'm squinting a lot tonight. I don't know what's going on. I shouldn't be blind. Let's see. All right. So I was doing roll. Let's go back. If anybody else has come in. Yep, Jolie's coming in. Perfect. I got only as far as Liz. I didn't make a whole lot of progress. Aaron is there. Hello, Aaron. Jolie,
Hello?
you're here, right?
Yeah, I'm here.
Okay, super. Annette, I think you're here.
I'm here.
Yep. Hasher, I think I saw.
Yes, I'm about
Okay.
to like leave and then rejoin because my laptop was kind of acting wonky, but like, yeah, I'll be
No big thing. All right. Mallory.
I'm here.
Hi, Mallory. Lainey.
Here.
Hi, Lainey. Camilla. No Camilla. Okay. Hannah Rao.
Yeah, I'm here.
Did I butcher that again?
No, you got that right.
Sweet. Okay. Diana's here. Grace is here. I was chatting with you earlier. Okay. Hannah W. Oh my heavens. No thank you.
I'm here.
Hi. Sorry about that. Apparently my dog wanted to say hello. And I think Stephanie's here too, right?
Hi, I'm here.
Hi. All right. Awesome. Well, gang, let's have a quick reality check. It is April 14th. We have one more week of lecture. And then here we are at the final on the 28th. So it's the final countdown. Legit, it is. So next week, I will be introducing the special project. The special project is something that you guys do on your own. You do not need to gather data. You don't need to write a full paper. All you need, and Aaron, I'm finding this kind of interesting here. I don't know what's going on.
It's either I'm sideways or the whole screen goes sideways.
That's
Yeah.
so weird. Oh, is it like an iPhone or an iPad?
Yeah.
Can you
So it's-
lock the screen to be the other way?
I mean, I could.
No, you don't need to worry about that. You just muted yourself. Oh no, you disappeared. I've angered it. Oh no.
There we go.
There we go. Hey, I provided technical difficulty troubleshooting. I don't usually do that. Okay, so next week I will introduce the project. It is a massive data set. Okay, when I say massive, like thousands of responses and hundreds of variables. You will be given special instructions. In fact, the lab this week was kind of a small introduction to that, where you will have, this week for the lab, you had a list of analyses you needed to do, and you needed to select which ones you wanted to use, okay? For the special project, it's going to be the same thing. There's going to be a list of analyses that you need to do, and you will need to select the variables to run the analysis. Again, I was quite kind in this lab where there was only one interval ratio variable. So that's what you needed to use for mean and standard deviation. With the other data set, it's massive and there are multiple options as to what you can do. So again, it is up to you. Part of what we've done also with our labs is having 1 to 2 sentences of interpretation. That is going to be a requirement of the special project as well. So I will go over all of that next week. You guys will have an opportunity to get started on it, and it'll be due the last week of class, which I'll probably make it due Friday at midnight as long as you submit it to me. I don't want this to be like a 6-7 hour project. That's definitely not the goal. The goal is to get the analyses done, copy over the tables or the results that you get into a Word document, and then write your couple sentences of analysis. So that's going to be separate from the final exam. Final exam is going to be a combination of open-ended, questions and some calculations that you need to run as well, where you need to show me your work. Ideally, you will submit all of your work through Course Connect. If there's any challenges, please email it, or you can shoot me a text and let me know that that's what you're doing. But I need to make sure that I can get a hold of it one way or the other. Questions about all of that? I just laid out a lot of information at your feet there.
So I'm sorry, I just wanted to make sure the final exam, like with the open-ended questions, that will be on the 28th?
Yes.
Okay.
Yep. So on the 28th, probably first thing in the morning, I'll make it go live so you guys can start working on it, and it needs to be submitted by the end of the 28th. We will not be having class. As I did for the other exam, my phone number is going to be at the top. So if you need to shoot me a text or you have a question, something doesn't make sense, don't hesitate to reach out. Obviously, be choosy about your question. If you're like, what's the answer to number 4? I'm probably going to be like, you're cute. We're not doing that. But any questions that, require clarification, if there's something that I'm not clear about, I'm not holding you guys accountable for that.
Thank you.
Asher, do you want to go in? I'm getting a request for you to come in. It's just a different device. Okay. All right, cool. We're about to be double Ashered. Okay. All right. Unless I just denied him, because now all of a sudden he just disappeared. There he is. Okay. Okay. So we are going to be covering, I want to make sure this is right. Did we cover ANOVAs last week, or we covered chi-square?
Chi-square, I think.
That's what I was thinking too. Okay. So we have ANOVAs left, and we have ANOVAs is chapter 11, and then chapter 12 is regression and correlation. So We're going to do chapter 11 today, and then chapter 12 will be next week in conjunction with the introduction of the special project. So let me get this open here. Oops, let's put it on the other screen. Let's have it start at the beginning and share a screen. Apparently I need to narrate all my steps today. It's just how the kind of day we're having. And slideshow. Can you guys all see that? Analysis of variance, ANOVA? Yes, okay, thank you.
Yeah.
Okay, and I think I am recording, but now I'm feeling anxious that I'm not. I am, okay. All right, so this is gonna be a chapter on analysis of variance. Now, it's not usually called all of that. It's usually just called ANOVA, this way, ANOVA. You occasionally will see MANOVA, so there'll be an M right here in front of it, and that's for multiple analysis of variance. So it's when you have even more independent variables that you are comparing against each other. For the purpose of this class, we are only going to dip our toes into the ANOVA pool because it can get quite complex. But ANOVA is kind of like the stepbrother of a crosstab. So just think of it this way a little bit. It's like if a crosstab married a correlational analysis. That's kind of what we're looking at here. All right. Why are we human? Yeah. Anyway, moving right along. Okay. So we will talk about how to apply a one-way analysis of variance. We're going to define the concepts of between and within total variance, because again, this is going to be a comparison of groups. So different independent variable, the different levels of them. And then within the same level of one independent variable, how they differ across levels of a different variable. So that's why we can do between and within analysis of variance. You'll be able to calculate and interpret a test for 2 or more sample cases with means. You'll be able to determine the significance of an F ratio test statistic. So this is what we're using for this. And I will show you what the SPSS output looks like. Obviously, we can't practice it because, you know, COVID sucks and we're not in class. But it's very easily done also in Excel. So I can show you guys how to do that. Okay, so just looking broadly, let me get my laser pointer. So far what we've been doing is the analysis of 2 group means or between and after scores. So we can look at what are the SAT scores for males versus females. Those are the 2 groups, right? So I would look at an average score on the SAT for males versus females. Or I could do a before and after. So this would be a pre and post test if I'm introducing some sort of intervention to see if there's been an improvement or decrease, or like improvement if we did a GRE prep class, right? What's your score before, what's your score after? So we're looking for an increase. Or what's the amount of depressive symptoms you have pre-therapy, introduced therapy, now post, hopefully we're seeing a decrease, right? So this would be comparing, again, either the group means or pre and post tests. But right now we want to know what happens if we want to compare more than 2 groups or 2 scores. You cannot use a t-test like we've been using before. It's not capable of handling more than those 2 groups or 2 sets of scores. So what do? Well, dun, 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 here comes in the ANOVA. So is there a difference in educational attainment among all 4 demographic groups? Okay, so this is from your textbook. It looks at educational attainment for these 4 racial groups that they identified. So they have white, Black, Asian, Latino, and then you see the sample size here. There's 6 individuals that they polled, 5 for Black, 6 for Asian, 6 for Latino. So fairly equal groups. And then you see the highest level of educational attainment. Could you do a t-test on this?
No, because there's more than one variable, or I mean, more than 2, sorry.
Right, there's more than 2. So what I've seen some of my doctoral students do before, they're like, oh, no, you can turn this into a t-test. You could do white, versus other, Black versus other, Asian. So you can combine them so that you end up with an other group, whatever that is, versus one type. So then you're comparing one specific group. What is an inherent flaw in doing that? Or can you think of something that might be problematic?
You lose a lot of like description and accuracy, I guess, because I don't know how to describe it, but
Well, I mean, it's just whenever you have any survey that says this versus all of these things that have clumped together, well, you lose any nuance that might be between these groups. You've just grouped them as others. So that's problem number one, right? We lose some of the complexity and nuance of the data. But the second piece is you have really uneven groups, right? Because here, if I were to do white versus other, right? I have the white group has a sample size of 6. If I combine all these scores, my other group now has a sample size of, what is that, 17? So I have really uneven groups, right? Which ideally we don't want to do. We want to try to have match groups. So looking at this, what is the independent variable and what is the dependent variable for this research scenario? What's the independent variable?
racial group.
Racial and ethnic group is your independent variable, and you have 4 levels of that independent variable. What is the dependent variable? It's the other one.
Education attainment.
Right, educational attainment, right? So the numbers that we've put in here, that's the educational attainment, okay? So the idea behind this research question is there, in fact, a difference between the level of educational attainment that is obtained based on your racial or ethnic identity? That's the question. Okay. So again, in swoop in ANOVA, it is an inferential statistic. So let's take a quick moment here and remember, there it is, inferential statistic. We talked about 2 different types of analyses when we do statistics. There's inferential. What's the other one? Do you guys remember?
Descriptive.
Descriptive is the other one, okay? So, oh boy, this is always a bad idea whenever I try to write with my mouse. Whew. That's a C. Okay, descriptive is the other one. What would be a descriptive statistics? It might be a frequency, right? It could be a mean. It could be a standard deviation. Those are all statistics that you run that will describe the data you have in front of you. Inferential statistics is somehow you're taking the data that you have to infer or deduce the progression of your dependent variable. Okay, so correlational analysis might be part of that. Obviously, an ANOVA is. We will talk later on about a linear regression. That would be another one of those. So ANOVA fits that bill. It is an inferential statistic technique that's designed to test for significant relationships between 2 variables in 2 or more samples. It's the same idea as a t-test, but extended to independent variables with 2 or more samples. Okay. So I can think about my other example over here. I can think of each of these as being samples, okay? That would be one way to look at it. All right. Yes, it also examines the differences between samples and within a single sample. And the differences can be referred to as variance or the variation, which is why ANOVA is an analysis of variance. So you're looking at a specific data set or sample and seeing how much it varies compared to another sample and how much it varies as it relates to a dependent variable. So we want to see how different they each are. So it's not quite a mean, it's how much they vary, okay? All right. A one-way ANOVA is an analysis of variance procedure using one dependent and one independent variable. That's one-way ANOVA. A two-way ANOVA, that's also called a factorial ANOVA. I've also seen it as just factorial analysis. It's an analysis of variance that uses one dependent variable and two independent variables. So you will see it as a 2x2 or 2x3, and it's usually, that's what you see as a square, right? You've got your two categories up here and your two categories down here, and the four possibilities. Occasionally, you'll see it as a 2x3, right? Like that. And again, it's almost like, again, we're looking at crosstabs. Crosstabs, though, is just a frequency. How many people meet each of these categories? This is beyond just a frequency, because a crosstab is, again, descriptive. This is looking at how much there's variance between the two, okay? A three-way ANOVA, again, is also considered a factorial ANOVA, but it's for one dependent variable and three independent variable, okay? So this gets trickier. So it's a 2x2x2 or 2x3x2, or so to speak. So I want to bring this home, and I feel like I'm going to use, hold on. I'm going to close this, and I'm going to end this for a hot second because I want to show you guys. I taught research methods this morning and this afternoon, where there are several really good examples of it. Let me find the traffic one. Because I think somehow with this, like if you have an example, it'll just bring it home a little bit more right here. Okay. Hang on tight. Now I need to find you guys. Oops. Can you guys see this? Okay.
Yes.
Okay. So remember when I was saying you could do, I don't know what's going on from current slide. It's quite curious because I cannot, here it is. I want to use my pen. All right. So when I was talking about, doing a 2x2 like this, I would take one independent variable here. That got weird. One independent variable here somehow. So this is how long does it take for people to brake, right? So it's the braking time, how long it takes them to react and brake. This gets kind of confusing, but let's make it a little easier first. So like for right now, just ignore this section, okay? So you're comparing younger drivers to older drivers. So this independent variable would be age, right? Okay, and you've got young and old. And then over here, it's cell phone use. So we'll call it cell. Okay, and this is, yes, they have a cell phone. No, they don't. Specifically, they described the study that it's a hands-free cell phone. So it's not like there's somebody going, hello, as they're driving. Also, they're not having them go on the road. Imagine like being at Dave & Buster's in one of those pretend simulation car. And then they measured it there. So you're in the simulation car, it's a hands-free phone, but you're talking to somebody as you're driving. How quickly can you brake? So the question is, where is there a relationship? You want to know about that, right? So is there a relationship between age and braking speed, or between getting distracted on a cell phone and braking speed? Okay. That would be a 2x2 because I'm using the cell phone use and age. I can make it a 2x3 by adding this. So now let me erase this so you can actually see what I'm writing, right? So erase that. Okay, good. Now we're taking into account whether they were in light traffic or heavy traffic. Okay, so we're adding another level. So what we see is in light traffic, overall, almost every category, they were able to brake faster than when it was in heavy traffic. Okay, So this is another independent variable that is having an impact on braking speed, meaning their reaction time to actually brake. So we're seeing three patterns here. So one of them, and this is not described in here, but just overall, younger drivers are braking faster than older drivers. If you're not on a cell phone, you're braking faster than if you are on a cell phone. And if you're in lighter traffic, you're braking faster than you're in heavy traffic. So this is, again, you're looking at multiple variables at a time. I just thought this would be helpful to just see an example. All right, let's go back to our actual lecture, which is not here. It is right here. Okay. So, and now why? Okay. So that's the three-way ANOVA. You can also do repeated measure ANOVAs, again, MANOVA, and NCOVA is again, it gets complicated. I don't even need to go into that. You don't need to know about that. Just if you see these variants, this is analysis of covariance, not just variance. So how do we go about doing hypothesis testing with an ANOVA test? Again, that's the whole point. We create these hypotheses based on theories. We want to test them out. So we gather data and then we see if there's a significant difference. So first off, there's some assumptions. So you are assuming that independent random samples are used, that you didn't stack the deck and just have, only one type of person in one group, one type of the other in the other group. So our choice of sample members from one population has no effect on the choice of sample members from the second, third, or fourth population. So for example, if you're selecting Asian Americans, that's who you're interested, that should have no effect on the selection of any other sample, right? There shouldn't be mixed in any way. The dependent variable is also measured at the interval ratio level. This cannot be categorical, okay? So that's something else we need to be mindful of. These are the assumptions we have. We also assume that the populations are normally distributed. So we can't confirm that 100%, but that is an assumption that we take with an ANOVA. And then we also assume that the population variances are equal. So the group with the largest variance should not be greater than 4 to 5 times the variance of the smallest group. So the idea again is I'm not going to pick a sample, right, whose population varies a ton and the other one who doesn't vary at all. You want to try to match them as much as possible. The way you would state the research and null hypothesis is the same as any other study. So your alternative hypothesis, or H1, is that at least one of the mean is different than the other. Now, I want to pause here for a hot second because this is where going back to the t-test, where you compare one group versus a conglomerate of the other group, allows you to see a more specific difference about that one group versus other. ANOVAs do not tell you that. They just don't. They will just tell you whether one of the mean is different than the other. So the way you would then see the nomenclature for your null hypothesis is that mean of population 1 or sample 1 equals the mean of sample 2, which equals the mean of sample 3, which equals the mean of sample 4. Okay. It can only tell us if there's at least one difference. It will not tell us which group is or are different. Okay. In order to run some of those analyses, you'll need to conduct post hoc analysis specifically on those groups to see which one is more or less than the other. Okay. So something to be mindful of. So the concept now between and within total variance, that is something that's quite unique again to ANOVAs. So the between group sums of squares, okay, and this is where we get into the math, so fear not, but between group sum of squares, which is labeled as SSB, sum of square between, measures the difference in average years of education between our 4 groups. So if we go back to our example earlier, the total years of education attained for the different racial groups, right? So that would be measuring the difference in average years of education between the 4 groups, right? Between groups, kind of makes sense. Sum of squares is the abbreviation of sum of squared deviations. And for SSB, what we're measuring is the sum of squared deviations between each sample mean to the overall mean score. Okay. Now the idea of within group sums of square, which is labeled SSW, sum of square within, measures the variation of scores within a single sample, or as in our example, the variation in years of education within one group. So amongst the Asian sample, what is the variation looking like? So I'm not looking across all of them between my groups. I'm now looking just within each group, how much variation is there? So SSW is also referred to as the amount of unexplained variance, and this is what remains after we consider the effect of the specified independent variable. The formula for SSW measures the sum of square deviation within each group between each individual score and its sample mean. Okay, so that's a lot of abstract talk describing what the formula is. Here it is. So the between group sums of square, here it is our SSB, okay? It is the sum of the number of cases in a sample. K represents the number of different samples, okay? So number of case in a sample, and this is your total sample that's found. Your Y of K is the mean of a sample, and this is the overall mean. And you sum that and square it, and that's your sum squared between groups. So again, it is the amount of variation in the dependent variable, which in this case is years of education, that can be attributed to or explained by the independent variable, which is the 4 demographic groups, right? The 4 racial and ethnic group. So again, this is important to note, ANOVA is actually a form of regression, which we'll talk more about next week, but you've probably heard that buzzword a little bit. It's kind of a predictive factor, again, inferential statistics. The within group sums of square looks a little different, right? So it is the sum of the difference of each individual scores minus the mean for that sample squared, okay? Another way you can look at it is also the sum of the squared scores for each sample minus the sum of scores for each sample divided by the number of cases in a sample. Okay, just one more definition, we'll be free here. The total sums of square, SST, T is for total, is the sum, again, of each individual score minus the overall mean squared, which will be the total of your sums of squared between and your sums of squared within. I'm sure some of you guys' eyes are rolling, glazing back in the back of your head, and you're like, what do I need to know about this with the whole? Okay, we're getting there. We're getting there. All right. So as if we thought we were done, we are not. So we need to calculate the degrees of freedom. Here we are again with degrees of freedom. So for ANOVA, we have to calculate 2 separate degrees of freedom because again, we're doing a 2 by 2 or 2 by 3. We have to see what it is. For the sums of squared between, the degrees of freedom are determined by, again, this is degrees of freedom. B is for between, because again, this is what we're doing. K is the number of samples minus 1. So in our example, what would that be? How many samples or groups did we have for years of education attainment and racial group?
4.
Right. So it'd be 4 minus 1. Degrees of freedom is 3. Pat on the back if you figured out 4 minus 3. Feel good about it. Yeah. All right. For the sums of square within, the degrees of freedom are determined, again, this is degrees of freedom W, because it is for the sums of squared between. It's the total number of cases minus the number of samples, okay? So in our example, I want to say there were 21. I'm not feeling 100% about that, but I'm pretty sure it was like 18, maybe 23. Okay, let's write 23. Minus K, which is the number of samples, which was 4, right? Okay. So it'd be 19. Okay. Next, what do we do? Well, the mean square between is what we need to figure out. So it's the sum of squares between divided by its corresponding degrees of freedom. So we would get this value, right? This is SSB, and we divide it by its degrees of freedom, B. The sums of square within is then divided by its corresponding degrees of freedom. So SSW, right, divided by degrees of freedom, W. So we're keeping things kind of in their own quarters there. So an estimate, the mean square between, is an estimate of the between group variance obtained by dividing the between group sum of the squares by its degrees of freedom. It's what we just did on the last slide. And this is just what I described. And the degrees of freedom within, we just described that, is your total number of samples minus 1. On the other hand, your mean square within is an estimate of within group variance obtained by dividing the within group sums of square by its degrees of freedom. We just figured this out just a hot second ago. Degrees of freedom within is your total sample size minus the total number of groups. The ratio now between group variance to within group variance is the F statistic, okay? Ratio implies what mathematical operation?
Division.
Division. So we are dividing, right? That's dividing, okay? The between group variance by the within group variance. Okay, that gives us F. Now let's talk about F for a minute here. It is used for analysis of variance. It represents the ratio between group variance to within group variance. And you will use the same thing as we've done before with a T or a Z statistic. There's a chart in the back of your textbook that will identify an F critical, and you compare that F critical to your F obtained. So the F obtained is the test statistic that you get by the ratio of the two. So once you divide your numbers, that's the F obtained. The F critical is the F score that is associated with a particular alpha level. What do we use for alpha? What do we always use?
0.05.
0.05, or if you like to think about it in terms of confidence, you could also say it's the 95% confidence, right? And the degrees of freedom within your sample, okay? This F score marks the beginning of the region of rejection of our null hypothesis. So if you're F critical, anything above that, you're able to reject the null that states that all the means are equal. So if your F obtained is greater than your F critical, you can say, I am 95% confident that these means are not in fact equal. That's what that means. Are we tracking so far? Does that make sense? Okay. So again, this is a critical F. This is the F obtained. So this is my critical value. Anything above that in the shaded blue, and I'm like, yep, they are significantly different. This is my obtained F. It is higher. Therefore, I can create my summary, which would be what? Do I reject or fail to reject?
Reject.
Reject. So based on these values, I would reject the null hypothesis that all means are equal, because my F obtained is higher than the critical F. Okay. Again, this critical value, much like any of the other test statistics we've done, states that from this value on, I'm 95% confident that those results were not due to error. Okay, I'm not 100% confident, I'm 95% confident. Okay. So quick summary. We start by just overall, the analysis of variance test examines the difference between 4 demographic groups and their average years of education. We go through and make some assumptions, right? Independent random sample, dependent variable has to be interval ratio, which years of education it is. We're going to say the population is normally distributed and the variance must be equal. Okay. Now I'm looking at actually these hypotheses. My alternate hypothesis is that at least one of the mean is different from the others. And that's all I can really say. I cannot, like, this would not be the statistic to be like, I think that African Americans or Blacks in that particular example we had have a higher level of education obtained than whites. This is just not a statistic that will give us that. It'll just tell us that at least one of them is different and non-equal, okay? Then my null hypothesis is the opposite of that, right? That they are all in fact equal. And then maybe I didn't say this earlier, so I apologize. So when we go through our steps, first we set our research and alternate hypothesis and null hypothesis, and then we always have to set an alpha level. Honestly, you guys always set it to 0.05. You can't go wrong with that. So that should just be moving on. That's what you do. Next, you're going to select the sampling distribution and specify the test statistic, I should say. We're going to be doing the F distribution and use an F statistic because we're doing an analysis of variance. Next, we need to calculate the between group and within group variation, okay? This is already all calculated for us. So yeah, this shows me, I think that's what I wrote earlier, it was 19. So the sums of squared between ends up being 63.03. The sums of squared within is 62.03, okay? Now to calculate the F statistic, I'm again taking the sums of squared between and dividing it by its degrees of freedom. Then the sums of square within and dividing it by its degrees of freedom. And then I get 21.03. I then need to divide it by, I want to say this is a multiplication. I need to go back because I want to make sure I'm giving you guys the right information. Boop, boop. I think that's it. Did I get that wrong? Oh, no, that's right. Sorry. So this here, I got myself confused with my own math. This is 21.01 and this is 3.26. I divide those two, right? Because the ratio, and I end up with a value. This is F equals 6.44. Okay. Now I need to make a decision. So in order to make a decision, I need to figure out what is my F critical. According to our number, so again, of degrees of freedom, right? And our sample size, our F critical is 3.13. So if I do, and again, this is kind of what an F curve looks like. So if this right here is 3.13, okay, this is my critical value. Anything in this shaded area, I can reject the null. So now my F obtained is 644. What do we think? That's like,
You
wait,
can reject it.
right. You can reject it because that's like way over here, right? So we can reject the null hypothesis and conclude that the groups are different in their educational attainment. Again, I cannot say which one has more or less. This is not the point of this analysis. It just states that they're not equal. They are not the same. Okay. We are not going to be doing effect size for this class. It's kind of beyond all of it. So we can kind of skip this right here. Now let's look at this. Again, this is frequency of emerging adulthood features across age group. This is what it would look like if you get a spit out here of SPSS and how you'd make sense of it, okay? So again, we have the frequencies of emerging adulthood featured across age groups. So these are the features. We have 5 features, and this is the different age group. Let me switch over here to my laser. The different age groups. So we've got late adolescent, emerging adults, and young adults. You see here the sample size is written for each sample, right? These are our 3 samples, and these are our scores on each of these specific measures, okay? So what we're doing is we are comparing the between group means. That would be comparing across this way, right? And seeing how they're different. And then comparing within groups would be we're taking this sample of late adolescents and comparing these means, okay? And then I compare the means over here, okay? What you see in an SPSS spit out, you would see this exactly. You find which ones are significantly different. And based on this analysis, they're significantly different at the 0.001 value, okay? So again, this would be the 0.1%. That's how confident you're feeling, 99.9% confident, okay? So there is significant difference in the scores for each feature across our 3 samples based on our F statistic. Does that kind of make sense? Questions? How can I help with this? Not getting a whole lot of talking back. So I don't know if you guys are super confused or if you're like, oh yeah, easy peasy, lemon squeezy. Seeing uneasy faces. Maybe you're like, what do I need to replicate? What do I need to actually know how to calculate? Would that be helpful? Yes. Okay. Gosh, I hate all my chicken scratch on all this, but honestly, being able to calculate what we described over here is going to be key. Where is it? Right over here. Okay. Being able to do, again, the sum of squares between your individual score and the sample mean. So why don't we, would it be helpful if we ran through an exercise just all together, maybe using Excel? Okay.
Yes.
No, I don't want to keep my, let me stop sharing. Let me get out of this. All right, give me a second. I'm just gonna plug this data in so we can do it all together. Whoops, that's not what I meant to do. Bring you over here. Okay. I'm just rewriting the data in Excel so we can practice this. Okay. Okay. Something is acting very wonky. Oop, it just opened again. I want to make sure that I'm giving you the right formula. Okay. Okay. I'm hoping you guys all have access to this. That's the only thing that's making me a little nervous. Okay. Sorry, I'm testing it out so that I can make sure it makes sense. Worksheet, that's fine. Of course, when I run it, now my numbers are different. So, oh, single factor. What am I doing here? I think this is right. Let me show. Are you guys still there? I can't see your faces. I feel like a
Still here.
crazy professor
Right
where I'm
here.
plugging away. Okay, this is what I've just done. Okay, this is the data we were looking at a minute ago, right? So this was, and I forget the order. What was the order? So this was white, Black, Asian, and Latino. So I put in the N for each and then the scores right through here. Now, are you guys seeing my Excel sheet? Hopefully you are. Yes, okay.
Yes.
If you're on home, this is what it looks like. You need to go over to data right here. And if you decide to do an analysis of variance for the special project, this is how I would recommend you run it. So you'd go to data, and on the very right over here, there's a data analysis button. If you do not have this button as part of your, the headings over here, you can go over here on the tell me what to do and type in data analysis tool pack. You just click on it and then it downloads it for free. And then you'll have this extra button. You then go over here and you would select single factor. So it's the very first one, ANOVA single factor. You would click OK. And then it has you select your input range. Okay. So, and I'm sorting this by column. So I've got these numbers over here. Now, the only thing that ends up being kind of wonky about this example, and I wonder if it's because, is that this is an N of 6, but obviously, do we have 6 results? We don't, we just have 4. So it's a little weird example from your textbook, but anyway, so you would click OK by highlighting all of your data over here. That's what's being done. Okay. And then if you press OK, you will, whoops. This is what you end up getting. So let me make this bigger. Can you guys all see this? Okay. Now I'm going to go back to the results that we got a second ago. It's not identical. That's the only thing with Excel. I'm like, come on, reproduce it. But I think what's happening is that they actually are calculating it through here from the textbook with all the count. And see here, our count, our degrees of freedom are going to be off because the total sample size is only going to be 16, when in fact, in our example, our sample size was 23. So it's causing some problem. But fear not, you have all the information, even if the information is not the same as over here. This is how you would run an analysis of variance. This is the critical piece. We have our F critical, which is pointed out as 3.49, which I believe is identical to what we got in here. It's at 3.13. Yeah, we can't win. 3.49 is what they say is F critical, and our F value is 6.91. Okay, so even from this, we would be able to say, yes, there is a significant difference, and we can reject the null hypothesis that the groups are equal. Okay, so what do you need to know to be super successful in the exam? Because that's what everyone wants to know. I will provide you with a table that'll look like this, and you will need to tell me whether you would reject or fail to reject the null hypothesis. Would you be able to do that if you had a table like this?
Yes.
Yes? Okay. Again, the key piece is you are comparing this F critical to your F obtained. If your F critical is smaller than your F obtained, then yes, you are good. You can reject your null hypothesis. Okay? If this F critical, let's create a what if scenario here. Actually, this is perfect. What would you do with this example? Could you reject? Let me make life easier because I think you guys are getting bogged down by one of them. Could you reject this?
No.
No.
Okay. Why not?
Because the F obtained is less than the critical.
Yes. Is everybody seeing that? Okay. This F critical is 3.86. The F obtained is 0.22 if I were to round. I cannot reject my null hypothesis because it's essentially, right? Let's draw it so we're clear on it. If this right here is my curve, this is my F critical at 3.86. And again, anything that's in this shaded area, we're good to go. But instead, I got 0.22. It's way out here, okay? It is outside of the area where I would reject the null hypothesis, okay? Now, let's erase this. It's so bad. Okay. Now, let's unhide and let's hide that one. What would you do here? This was a repeated measure ANOVA. That's why we had two responses.
Reject.
Okay. And how do you know that?
Because it's the F critical is smaller than the 5.56.
Exactly. Okay. So if I go back over here, right, I have my curve, looks something like that. This is my reject line. My critical value is 3.86. It's right here. Anything over here, and I reject. And now my F obtain is way down here at 5.56. So yes, I can reject my null hypothesis. I reject the fact, again, per null, that all the means are equal. This is suggesting they are not all equal. Okay. Kind of makes sense? Okay. What else do you need to know? Let's go back to this screen share over here so you guys can see my doodling. Okay, reviewing of key terms. Can you guys see this? Yeah, okay. So you need to know, again, what's the difference between F critical and F obtained so that you are able to actually see if there's something, significant or not. You need to know what is an analysis of variance. Like, what is it we're doing? What does it mean, like, conceptually? Again, we're analyzing the variance between group and within group to see if there's a significant difference. That's what we're seeking to do, okay? You need to also recognize that your mean square between or your sums of square between are going to be related to your degrees of freedom between. Sums of square within are going to be related to degrees of freedom within. I think we talked about that just a few slides ago. Right here, degrees of freedom within, degrees of freedom within, between, within. I feel like I'm saying the wrong words now. Those are the take home for that. Knowing how to do it in Excel will help you if you select that analysis for your special project. Obviously, there's not going to be any Excel in the final exam. It's going to be more broad understanding of what we're looking at. Okay. Questions? Oh, somebody wrote something in the chat and yes. Hannah, you had a great question several minutes ago. Sorry about that. Can F critical be the same as the F obtained? Yes, it is an inclusion. So like your critical value, it is that value and above. So if your F obtained lands right on the nose to your F critical, that's fine. Does that answer your question?
Yeah, thank you.
Okay. Any other questions? Okay. Those of you who did not get a chance to complete the lab because you couldn't access the data, hopefully you can do that now. And then we will see you next week for the last lecture and the special project. So just come prepared because it's about to get busy next week. So we're going to keep it lighter today in preparation. Sound good? All right. You guys have a
Thank
great
you.
evening.
Thank you.
All right. Bye-bye.
Thank you. Thanks. Have a great week, Professor.